Hi, thank you, everyone. My name is Mark Littlefield. I'm a Vertical Product Manager for Defense at Kontron America. And for today, I wanted to talk to you about something that's happening in the community that I think some of you at least might be interested in. And it gives me a chance to kind of reach back into my history, my experience working in the VPX community over the last 15 years, close to, I guess. And some of the things that have been going on in the last, say, 18 to 24 months, and it's pretty exciting. So my topic is VPX for Defense Open Systems Architectures. And I'm going to talk about the process we've been following recently, some of the difficulties, and where we're going from here. So standardization is a natural development as markets develop. I mean, we all know that. As a market emerges, things are kind of wide open, sort of Wild West. People are trying things out. Innovation is happening all over the place. But as time goes on, people are finding best practices. They refine their approach to their products. And as standardization just kind of evolves out of that. Now, standardization can be either formal in the form of like a committee that gets together and writes a document that everybody agrees to follow, or it can be informal. Something like the Intel ISA architecture came because of the market dominance of IBM. But they're still standards, and it's just a natural form of the market. So there's a bunch of good examples out there. I picked a couple to highlight some of the things that really benefit open architectures. One is the ATX, MITX family of standards. Community's pretty familiar with that. It evolved out of the desktop community. It follows standard footprints, standard power profiles, standard feature sets, standard apertures for I/O. But another example that's maybe a little closer to VPX and some of the things that some of the problems this community tries to solve is COM-E. In COM-E, there's 4 standard footprints, although 3 are the most common. And then there's standard connectivity. Now there's 8 different types defined by standard, but really only 3 are really common. And there are 3 that are aligned along certain product needs, certain industry needs. One of the key things about COM-E though, is that there's no user-defined pins. Everything is defined on the connectors. So what is kind of the secret of these successful standards? And I'm using these 2 as an example. There's plenty of other examples out there. You rigidly define what makes sense to define. So it could be the footprint, the physical footprint, where the mounting holes are, where the keep outs are, what your envelope is, and so on. The I/O. You define your I/O. Any board is going to look the same as any other board to what it's talking to. The power, you want to be able to predict what the power is going to look like and what pins it uses, how much it's going to draw, and so on. A minimum feature set. You want to have a basic capability that is going to be there on every product. And then use cases. You define a set of use cases and you say, industry, follow these use cases when you're building your systems, when you're defining your products. But you also have to allow for innovation and differentiation within that envelope of things that you've defined within the standard. That can be the processor, the type of processor, how powerful the processor is, what features the processor has. Expansion, you might have onboard expansion that you can provide. Application domain features. You might want to put a specialized processor on there or a CPLD or an FPGA on there to provide capabilities that your competitor over there doesn't have. So defense, however, has difficulties with standards. There's certain real problems for trying to standardize in a defense environment. One is orders of magnitude differences in like bandwidth requirements and things like that. You have some cases extremely small latencies that have to be attended to. So you can't, there's limits to where you can abstract. Different architectures. Just take a look at the example here in the pictures. A ground-based radar is going to have a different architecture than a UAV-based EO/IR sensor. It's going to be different than a wide-body SIGINT platform. You know, there's just real differences in the way that systems are going to be architected and the requirements that those systems need to meet. And then lastly, and I guess obviously, is that you've got environmental considerations that vary widely. Again, a high altitude UAV is going to be much different than, say, a ground-based radar or something like that. You know, you know, even looking at more extremes than that, you've got like an EW system sitting on the tailplane of a fast jet sitting right next to the engine exhaust. You know, that's pretty harsh environment. How are you going to standardize across this wide range of environments? Well, VPX has been around now since about the mid-2000s. It's been pretty successful at what it's tried to do. When it was first defined, it was focused mainly on the physical nature of the standard, the form factor of the board, the electrical characteristics of the connectors and so on. It focused a little bit on the functionality of the board, mainly around like the utility plane, the power, certain signals that are common among the boards, things like that. Then in the late 2008 timeframe, OpenVPX started, and some of you might remember I had the honor and privilege of being a co-chair, one of the two co-chairs of OpenVPX in its first incarnation. And we tried to extend VPX to address those functional, try to standardize some of the functional implementations that the market was gravitating towards. So let me focus on OpenVPX for a moment. I would call it a qualified success. There were certain things that we did really well, certain things that have endured. Some of those pros are, we introduced this concept of communication planes that's pretty well adopted now and everybody's pretty happy with. We further refined the utility plane that I mentioned before. I was particularly happy with that one. I spent a lot of time and effort on a lot of calls to do that. And we created kind of a standardized way of defining module slot profiles and chassis profiles and things like that really endures. However, and this is my opinion mainly, and I'm sorry if I'm stepping on anybody's sensibilities, but I think that we fell short. I don't think that we were the full success that we would have liked to have been. Basically, we didn't succeed in the goal of creating a universal slot definition. And I'm going to argue that it's not possible, but we could have moved a lot more closer to that. And I think we fell short. And we did the community a disservice, in my opinion. All the profiles, I think without exception, there may be a couple of specialized profiles, but I think all of them have user-defined pins. User-defined pins are a real detriment to interoperability and, say, upgradability and things like that. And for promoting an open system architecture, it's really a bad thing. And there's many, many, many profiles in OpenVPX. If I counted right, I counted 30 6U profiles. These are just slot profiles, not module profiles, because the module profiles say, okay, you've got these pipes, and this is the protocol that you put on these pipes. Ignoring all of that, I counted 30 6U and 63 3U slot profiles in the standard. That's not very conducive to an open system architecture. So SOSA is a real effort by the community to address this. Now, SOSA goes far beyond slot profiles, but I'm going to focus on kind of the slot profiles and its impact on VPX and why I think what we're doing in SOSA is a good thing. So the Department of Defense, and I'm going to read this if you don't mind, because I love this bullet, has a strong desire to enable easy and rapid technology upgrades and updates in fielded defense platforms without removing the entire system. So essentially, and if you can see in this picture here, you've got a platform like an aircraft that's going to be out there for 35, 45 years, and it's not going to have the same electronics that it started with. You're going to have upgrade cycles. And the desire is to be able to upgrade those systems at the natural pace of the technology that the system is built from. So an SBC might upgrade at 3 to 5 years. A specialized processor maybe at the 5 to 9 year cycle, where the chassis itself you may only upgrade once in its 35-year life. And how do we do that? We've got to create a structure, a set of standards that people can design to, and a market that can feed that community. So how is SOSA doing that? Well, there's a number of things. We're defining, how do I say? Well, number one, we're doing away with user-defined pins. That'll move us a long way. But there's other things that we're defining, like Ken Grobe from Elma talked about how we've taken away the freedom of being able to swap between 5 volt and 12 volt, and we've gone to 12 volt centric boards. That next to the user-defined pins is probably going to go the longest way to keep a common platform alive while being able to do model year upgrades on certain components within the system. There's other things like clocks and other specialized signals that we've put real bounds around and said, if you're going to have that, this is how you're going to implement it. That takes away a lot of the variability within these systems. The net result is we're defining an open architecture for defense that will work. One of the key things that we're trying to avoid is trying to solve every problem within the defense community. The one thing that one of our sponsors keeps bringing up is an 80% solution. We're solving an 80% solution. If somebody comes up and says, oh, well, we need this special corner case, well, we make conscious decisions to say, well, no, we're not going to attack that, because by attacking that, we're going to disrupt the rest of the market. 80% solution is what we want to achieve. What are some of the challenges that we're facing? We have different technical requirements for different types of platforms. The defense systems are just different from industrial platforms or medical platforms. There's you know, I already talked a little bit about some of the bandwidth issues and the latency issues and the ruggedization that just don't exist in those spaces. There's a ton of different applications. There's radar, there's EW, SIGINT, there's sonar, there's just a huge, broad range of applications. Ground-based, air-based, unmanned underwater vehicles. There's a ton of them, and each one of them bring their own set of technical requirements. There's legacy systems. We can't expect that people they will define a new way of doing things, and all of a sudden everybody's going to rip out the guts of their airplane to be able to accommodate this new way of doing things. Well, no, we have to accommodate the aircraft, and so we have to figure out how we create an open system architecture while being able to maintain compatibility to these legacy systems. There's different ways of implementing systems, and one of the things that I always found really interesting is that the different modalities, you know, the radar community implements systems differently than the SIGINT community. And, you know, you put them in the same room and say, okay, we're solving the same problem here. Well, we do it this way. Well, we do it this way. How do you come up with a common approach for building these systems across these different modalities? And then lastly, you know, we have, well, way more than 10 years, more like 15 years worth of experience in VPX adoption. And both within the modalities and within the vendor community, we have our own ways of doing things. And how are we going to bring all of that together and come up with a common approach? So, VPX itself is different than some of the other open system architectures that you might see in the community. When you compare it to, say, COM-E, what do you have in COM-E? You have a processor module. And what do we have in VPX? We have processors, we have switches, we have specialized I/O. We've got specialized peripherals like, say, a GPU for an attached coprocessor. We have things like radio clocks and special hybrid boards. You know, it's no longer, it's clear we can't have a single standard for a single slot definition that, you know, any board we can pull off the shelf will fit into that slot. It's just not going to happen. And then within these classes, we've got different kinds of boards that we have to be able to support. How do we define this? Well, Clearly, a universal definition is impossible. So what we need to do is we need to come up with some minimal subset. What we need is a taxonomy for defining functional board types, some sort of a hierarchy of breaking down a board so that it fits into a class that we can all recognize and that we all know how to work with. SOSA didn't do this directly, but we got there in the same by starting with the CMOS and host profiles, which Ken talked about earlier. We used those as starting points. We collected a lot of information from all the participants, the vendor community, the integrator community, the government community, and tried to sort of class all of those competing thoughts and needs and what have you. And again, using that rule of thumb of 80%, tried to fit them all together. And then we crafted solutions by refining all of that. And the result was we now have a set of profiles. It's effectively a minimum set that meets that, again, that 80 percentile need. So I'm not going to go through all of them. It'd take us forever to go through all of them, but I'm going to show a few examples. Start with 3U SBC. 3U is a little challenging because of pin limitations. There's just so many pins on 3U. 6U has more pins, it's a little bit easier. But 3U, there was a lot of discussion around this. So what we came up with, and it was clear that there was multiple competing requirements that we had to meet. So there was no one slot profile we could meet. There's modern general purpose SBC that has things like USB and SATA and XMC mappings and things like that we all expect to see on sort of a general purpose SBC. But then there's high performance SBCs. You have an FPGA-based SBC. You don't need all of that USB and 1000 base T crap. You just want fat pipes in and fat pipes out. You have specialized processors like receiver cards. Yeah, well, there's no reason why they couldn't use the same kind of slot profiles, but they have different needs. They have RF they have to bring in, or optical connections you have to bring in. So what's the solution? What we did is we find two basic slot profiles. One is what we call an I/O intensive. Let's use the little button here. I/O intensive, where it's focused on sort of those general purpose types of signaling that you'd expect on an SBC. Basically bringing your common computer into an embedded environment. But one of the key things here also is the XMC mappings. We wanted to be able to support XMCs, so that's in here. But like I said, certain other boards, like a high performance FPGA board or a receiver card, doesn't need all that. So what we defined is a primary and a secondary compute-intensive RF profile, where we did away with all those standard I/O and replaced it with fatter pipes, either 16 pairs of expansion plane or 32 pairs of expansion plane. And you can see that these two are identical, but with the exception of the top half of P2. With this minimum set, we've defined a way of building 3U SBC or 3U computing systems. So taking that up to 6U, 6U again was a little bit easier because we had more pins to work with, but even here there was some conflict that we had to resolve. You can see we've got pretty big fat data pipes here, got nice big expansion plane here, we've got our general purpose I/O down here, and then XMC mappings, plus a couple of apertures for things like RF or fiber. But even that had some concerns. There were systems where, say you wanted to put two large FPGAs onto a 6U board like this. Well, maybe that 32 pairs isn't enough. So I don't need an XMC on here. This is just big computing engine. Well, why don't we replace this with this? So even here we had to compromise a little bit and come up with a secondary profile. But these are close enough that you could conceivably create a universal backplane that for some future expansion, replace one board with another board and expect it to work. Now, certainly the Defense Department would love if we could just pull a board out of one generation and pop another board in from the next generation, and it would just work. Maybe we'll get there, maybe not. But at the very least, what we're doing is we're going from something that today takes months to years to develop and field and upgrade to something that we maybe can do in weeks to months. And right there, we have a net savings. So, and now that I was just talking about the definition of the pipes. We went so far as to define the module profiles that will go onto those pipes. What connectivity? Basically, just for this, mainly for information. Things like 10 and 40 gig E for the data plane, 10 gig E for the control plane, PCI Express Gen 3 for expansion plane. We've also defined all of those user standard IOs, things like USB and so on. But then we've also, again, recognizing that we have legacy systems that we have to be able to support, we've captured things like PCI Gen 2 rather than Gen 3. We've got Aurora for those kinds of systems that are doing FPGA to FPGA communication. So there's provisions for things like that. So I mentioned earlier that SOSA is a lot more than slot profiles. Absolutely, way more. But I focused my talk on this, but I did want to give a nod to some of the other efforts that are going on in SOSA. There's an electromechanical group that's focused on kind of how the system is connected to the outside world and what its internal connectivity looks like and so on. There's an architecture, how you build from a software and a systems approach, how you build these systems. There's a software working group. There's system management and security working groups. There's a business and conformance. Conformance is a big question. And in fact, we haven't even really started to address that. That's a problem for 2019, is how do we test for conformance, test how products meet that standard, and how integrators can be expecting to be able to buy from vendor A and know that it's going to work in their systems. And then lastly, there's some application domain subgroups to kind of test the standard against the domain. One group I work with is the radar group. We're testing the hardware, the software, the architecture, how all of that, how you can build practical radar systems using this. The results are, again, a complete common infrastructure for building and maintaining over generations high-performance defense sensor processing systems. But at the same time, we're also developing a market for supplying these components. And that's the thing that, for me as a supplier, I'm most excited about. We're, in a real sense, developing a market here that is not going to be just sensor systems. It's going to go way beyond that. So these impacts of this effort, certain classes of products are going to be commoditized, okay? And people look at me and go, as a vendor, how am I happy about that? I'm thrilled to death. I will gladly trade commoditization and some points of margin for a market that doubles or triples in size because my customers are upgrading their systems at a much higher rate. I'll trade it any day. That'll also allow me to focus on new types of products and new features of products that I maybe couldn't do otherwise by trying to maintain my own niche and my own customer base. And that's going to just benefit the integrators. They'll have new types of products to choose from. The easier, cheaper sensor upgrades, as I mentioned, will drive that faster upgrade cycle. More business for us. I'm happy by that. And then lastly, even beyond SOSA, what I think we're going to find is that the overall market is going to benefit from using these design principles. Nothing we're doing here is so specialized for defense sensor platforms that they can't be applied to other types of problems. And Kontron, we do a lot of our work, in fact, a pretty sizable amount of our work outside of the defense space. Transportation is probably on par right now with our defense business, and they're going to benefit from this. So this is my last slide. Going forward, I say here Snapshot 2 is released. In fact, it's not quite released. It's supposed to go out this week. I think final approval is like any day now. So please watch for that snapshot. Take it, download it, look it over. If you have thoughts, let us know. We're already working on Snapshot 3, or we may end up going to a 1.0 release. We're not sure exactly yet, but that work is underway. I myself, I'm on probably 5 calls a month. 5 calls a week on this. Kontron, as well as several other vendors, are working on our first generation of products developed in alignment with the SOSA technical standard. That's the words we're supposed to use. It's a little sensitive because there's no conformance policy yet, so we can't really say that we're compliant or conformant because we have no way to show it. So that's what we're allowed to do by our agreement with the organization. But we've already announced our first product. We've already shipped our new first product to several customers. We've got other work underway. I saw that Annapolis Microsystems has product that they've announced that's in alignment. I think Elma's announced product that's in alignment. We're going to see more coming in the months. This is a fast-moving train. The conformance program is expected to launch later in the year. In fact, like I said, that's probably the #1 thing that we have to work on this year. That'll provide a mechanism for testing and certifying that products meet the standard. And I think there's ideas that there'd be like a catalog that will be maintained of products and their test results. Several plug fests are being planned for this year, and I know, are looking forward to participating. And the idea there is we want to demonstrate the effectiveness of the standard, and as well as raising confidence within the community that the standard is real, that it has benefit, and then it works. And then finally, even when we come out with 1.0, the standard is expected to evolve. It's not going to stand still because the technology isn't standing still. We want to be able to address the next generation technologies and the lessons that we've learned from this, Rev 1.0 of the standard. So I personally am really excited about this. I think you could probably sense my excitement about it. I think we're righting some wrongs and again, my personal opinion, we're righting some wrongs that were done in the community some years ago and that I helped to cause. And I hope that you all see the benefits and reap the benefits of our hard work.